Bismillahirrahmanirrahim. Today I am going to start a lecture on diazonium salts, diazonium ions, how they are produced, how they are synthesized, what is the mechanism behind the synthesis, and then further how the diazonium salts are valuable in synthetic chemistry, in organic synthetic chemistry, how you can use them for the preparation of different compounds. So let me start the diazonium salts, diazonium ions, what they really are. In previous lecture, that was on the synthesis of an introduction or a synthesis of azo-dyes, where I use diazonium salts for the preparation of azo-dyes. In that very aspects, I thought I should have given you a lecture on the preparation of diazonium salts. In that very respect, one should know the mechanism behind the synthesis of diazonium salts. They are important for the preparation of the dyes, colorants, the color producing molecules, they are important electrophiles. So students, undergrad level students, should have an idea how the electrophiles are produced. Further, those electrophiles could be used for electrophilic substitution or electrophilic addition reactions. So in this reaction, I'm going to convey about the preparation of diazonium salts. Previously, I discussed there the use of amines, aryl amines, and then I told you that one could use NaNO2 plus HCl to produce diazonium salts, something like that. And those salts were subsequently reacted with other aromatic compounds for electrophilic substitution reactions, resulting in the formation of some new azo-dyes. So today I'm going to explain the synthesis of this one. I'm writing it in a general form. I would write amines, substituted primary amines. We react them with, in fact, NaNO2. We use HCl to generate diazonium salts. It's supposed to be like this. The diazonium salts. That's very perspective. In fact, these two bodies react with each other in the beginning, in the first, when we add them into the beaker, into the reaction mixture. What happens really, if I write this formula like this way, Lewis dot formula, we have an idea, the HCl and this body, they do react with each other. This oxygen, which is a negatively charged, this gets protonated with a reaction with HCl, and it becomes OHN O, something like that. Okay, in the first step, when we add NaNO2 plus HCl, this HCl protonates one of the oxygen in this group, in this compound, to give you this one. We have still HCl around in the beaker. Then one of the proton again gets attracted by the lone pair of oxygen, resulting in the formation of like a water molecule in this way. I would write the other way. So it results in the formation of water and then we have this sort of a molecule. This gets positive charge. In order to neutralize the positive charge, this is attracted towards here. Water molecule leaves, giving us positive NO species along with the water. So once we start diazotization of any alkyl and aryl amine, we introduce NaNO2HCl into the beaker. These two bodies react together through fluorination of the oxygen twice, resulting in leaving of one water molecule, leaving NO positive, nitroso in the form of positive. It's an electrophile now. It is generated out of these two bodies, Then this NO positive, it approaches this. I can expand the two protons written on with it like this way. It approaches through the primary amines. Then this lone pair moves to this one to make a bond between nitrogen and nitrogen. So what happens, in fact, we receive this sort of a product there that's in the beaker. So this is how the reaction starts in the beginning. So what happens as a result of the reaction between NO positive and an amine, the nitrogen is supposed to get the positive charge. In order to neutralize the positive charge, we introduce some sort of a base over here. This base has the capacity to capture, remove and exclude one of the proton from here. So one of the proton is captured by the base, and this electron from the hydrogen that is given to the nitrogen, resulting in the neutralization of the positive charge. So we will have something like that. So it will happen like this one. At this point of time, the HCl is inside the HCl is inside the beaker that can come to chlorinate the oxygen, really. That is, now what happens really when we put in HCl, and actually the HCl is already present inside the beaker, excess of electron. We have an idea, there's a one lone pair, it moves between nitrogen and nitrogen. As a result, it's a drive for the reaction, for the capturing the proton. Then we will have something here, NHO, something like that. It can happen like that. The protonation of which the protonation of oxygen gives us N-hydroxy azo compound. It gives N-hydroxy azo compound as a result of this one. Then what happens really? A protonation of the OHs had happened over here, resulting in the formation of N-hydroxy azo compound. Then there is another reaction there of the base molecule. There is another availability of the HCl is there in the beaker, so there could be the protonation of this water molecule. So let me explain you what has happened here. So once we reacted this anion along with HCl, of the reaction of these two bodies generated NO positive charged species, which reacts with the lone pair of the nitrogen, giving you this sort of the compound where nitrogen carries positive charge. This positive charge has to be balanced. We pour in some sort of base which removes one of the proton, resulting in the balancing of the positive charge. We then, the presence of the HCl inside the beaker protonates this protonates this oxygen, and again this nitrogen becomes a positive charge. If we put in some sort of base, it rips apart this bond between nitrogen and hydrogen, and resulting in the formation of this sort of a compound is in this fashion. Again, as we have an idea, the presence of HCl inside the beaker is a sort of an excess amount of HCl is present inside the beaker, that's always available. This HCl again gets provides proton for protonation of the hydroxyl group. What happens then? You have this sort of water molecule formation having some sort of a positive charge. Then, in order to neutralize this positive charge, this lone pair moves this way to generate a triple bond, and the water molecule leaves out, giving us N triple bond N, and this bears positive charge. This is called diazonium ion. This is called diazonium. This is called diazonium ion. You know, one can see very clearly this is called diazonium ion. I can explain it a bit again for you guys. I've told you the N reaction between Na and NO2 is supposed to be something. It's negative, it's a positive species. HCl is present in the beaker. This proton is attracted by this one, and we receive this sort of a species here. Then again the presence of HCl inside the beaker, inside the flask, this is also attracted by the lone pair. It gives us this sort of the compound. Oxygen carries positive charge. In order to neutralize this one, this bond moves this way, leaving water out, resulting in the formation of NO positive, and this species in fact comes to attack at this amine to give this sort of a product in which the nitrogen is supposed to carry the positive charge, because the valency exceeds to 4. In order to neutralize the positive charge, we put in some sort of base which removes one of the proton from the nitrogen and balance this positive charge out, giving this sort of species. The presence of further HCl and the movement of the lone pair and the capturing of the proton results in this formation of this molecule, which is called N-hydroxy azo compound. Further, in order to neutralize the positive charge of this nitrogen, which carries positive charge, base is introduced. It removes the proton, generating this sort of product. Then again, the presence of HCl promotes this hydroxyl functionality, creating a water molecule having a positive charge, and this water molecule leaves from the system, leaving behind a triple bond between nitrogen and nitrogen. This is called diazonium ion. You know, this is our diazonium ion. We have an idea in the system we are using HCl in excess, where protons has been used in the protonations, and its counter ion HCl chloride is available in the beaker, so it will be attracted by this positive charge. So this is called then diazonium salts. So diazonium ions counterbalanced by chlorides, they are called diazonium salt. Diazonium salts. So this is how the diazonium salt is produced, starting from a primary amine reacted with NaNO2 with HCl. In fact, the reaction proceeds with the reaction of these two species with each other, resulting in the formation of NO positive, which then gets entered into the as a reaction species and reacts with this amine, and the subsequent steps are here, which I've explained to how the diazonium salts are formed. So this is how the diazonium salt is produced at the first diazonium ion, and then counterbalanced by the presence of the chloride. They are called diazonium salts. Now let me explain about what sort of amines could be used for the formation of, for the preparation of diazonium compound, diazonium salts. Unfortunately, an an R group. It could be anything, you know, at the moment it can be an alkyl. It can be anything like CH3 and amine. It could be something like that. It could be, yes, it could be something like that, or their compounds could be some sort of aromatic amines like aniline, as the species, the compounds contains primary amines on aryl or alkyl amines in the form of primary structures. Primary. They are supposed to produce the diazonium ions or diazonium salts, diazonium compounds. If you have a starting species as a primary amine, why primary? Why not we can use the secondary or tertiary amines? To explain that, just so you people have an idea that why only primary is preferred over the others. Let's say, as I've told you, we have some sort of an amines. I can expand these bonds just to make it more clear. Primary amines, and we have an idea this body comes from the reaction between NaNO2 and HCl. How it generates, it is very much clear to you guys now, along with water. So this body comes here for the reaction, you know. So if the primary amine, the reaction proceeds the way I have just explained to you people. However, if one of the proton has been replaced by any other substituent, being the amine is now primary, again, what could have happened? Yeah, the nitrogen still carries lone pair. The lone pair can move to attract the electrophile. Yeah, then we have proton, and we have a NO over here. Resultantly, this body is supposed to carry the positive charge, you know. And at this point of time, we used to introduce some sort of a base because we want to neutralize the positive charge. So the base removes the proton from this amine, leaving the structure with balanced charges, you know. The nitrogen will have no more positive charge, so we will have something, this sort of compound. We have still here the presence of HCl in the beaker, but as this nitrogen does not carry any other protons, so the reaction will stop here. There won't be, it will not proceed anymore. There won't be any reaction. This will be the product. this will be the product. You won't get the diazonium salts because there's no more proton is present on nitrogen. So we will have a nitrosoamine as a product. But no diazonium salt. But no diazonium salt because there is no more reaction in the subsequent. No more reactions is possible because no more proton is available that can accelerate, that can make the reaction to proceed in the forward direction. So this is how the reactions will not be possible when the amines carry the amines are secondary amines, they're not the primary amines. So this is how it could be. The product will be the nitrosoamine only, but there won't be any subsequent reaction steps involved, so one cannot get diazonium ion or diazonium salt. Let me go back again. If we have a tertiary amine, let's say we have all R groups around the nitrogen, no problems. We have an idea. This species, the electrophile, comes closer. These lone pair of the nitrogen, they do attack at the positive charge site, and subsequently what happens, we get this sort of species, you know. Three R's are around. Lone pair has attacked at the nitrogen, the positively charged nitrogen, resulting in the formation of a bond. Now there are 4 bonds over the nitrogen, so it will carry positive charge. If we put in base here, as we did in the last time, the base is there to remove the proton. We can remove protons using base, but at the moment the nitrogen does not carry any proton. So it will not remove any proton out of the dye to neutralize the positive charge. Then what is supposed to happen then? Then it's supposed to happen then the nitrogen, the bond between nitrogen, it will move towards the nitrogen which carries positive charge because it has to be neutralized. We cannot put in base. I've put in base, even then there won't be that sort of reaction because the base cannot subtract those, you know, proton. No proton is available. So what happens then? Then we will have nitrogen, we will have R, we will have, this has moved here. So what happened? This has lost electron. So what is this? These are the ones where we have started. This is the starting compound. This is the starting compound. Means there is no reaction at all. The generation of the starting material confirms there is no more reaction, and it has happened in case of when we have tertiary amines. No diazonium salts. Similarly, there were no diazonium salts from the secondary amines, only primary amines. They're supposed to produce diazonium ions and then subsequently diazonium salts. However, the secondary and tertiary amines, they are not supposed to produce the diazonium salts. I've already given you the examples. The amines could be of any type. These R's could be the alkyl parts. Let's say they could be CH3, CH ethyl groups around, and we ask them to diazotize using NaNO2 plus HCl. We have an idea, as I've told you, there won't be any product as per the above criteria. Or let's say we have some sort of benzene ring over here, we have some sort of ring another here, we have a CH3, again 3 substituents available, no more reaction is supposed to be there for the formation of diazonium salts. Similarly, if you have only secondary amines, yes, there will be a reaction, but the preparation of nitrosoamines and nitrosoamines, but there won't be the possibility of production of the corresponding diazonium ions or diazonium salts. So this is how one can get an idea why you can't use secondary and tertiary amines for the preparation of diazonium salts. Only the primary amines could be used for the preparation of diazonium salts and the diazonium ions. Once we have performed, let's say, the diazotization, we in fact produce this sort of species. These are the species where nitrogen carries positive charge. They are supposed to be the electrophiles. Species having positive charge, they are supposed to be the electrophiles. So what they could do, they could be used in a normal routine electrophiles as electrophiles for electrophilic substitution as well as electrophilic addition reactions. These electrophiles is frequently been used for electrophilic substitutions on benzene, for the preparation of azo-dyes. The reaction between diazonium ion and the benzene. We have an idea this benzene nitrogen carries positive charge. In order to neutralize this one, the lone pair moves over here. Giving us this sort of structure. The terminal nitrogen in fact becomes positively charged entity, so it can be an electrophilic center. It could be attacked by the pi electrons or so-called double bond of the benzene over here. So I've given you in one of my lectures how benzenes undergo electrophilic substitutions. One of the proton will be replaced by the incoming electrophile, so the product is supposed to be the electrophilic substituted benzenes where one of the proton has been removed from the benzene. So this is a sort of an azo group, which is basically the requirement for the preparation of azo-dyes in textile industry. So once we have synthesized this species, the diazonium ion, the diazonium compound, diazonium salt, we can have this body, and this could be reacted to an aromatic compound. This aromatic could be a single benzene, some sort of benzene substitute, some sort of compound, functional group. So we have an idea this body will act as a directing group. Either the group could be the earth and para directing, or it could be a mara directing, depending upon its chemical nature, whether it's a withdrawing or it's a sort of a donating group. So as per its chemistry, it will direct the incoming diazonium ion to either artho or para group. So this will give us a substituted benzene. The substitution will result in the form of a azo compound, which is supposed to be the colorant. This is how one can produce the colorant. It could be something like that, or it could have some sort of withdrawing group. Still, electrophilic substitution could have happened. We could have these sort of compounds, or this sort of we can have these sort of compounds. We can enhance, we can introduce some other groups on the benzene rings. So whatever they are either directing, they are either donating or withdrawings, they're either withdrawings or donating. So as per their chemistry, they are supposed to direct the incoming electrophile at different positions on aromatic groups, so different product could be obtained. This is how the diazonium ion could be used as an electrophile, and this electrophile can be made to react with benzene under electrophilic substitution for the preparation of colorants, color molecules. The colorants could be generated. Colorants could be produced. Why colorants? As we have an idea, the reaction between this electrophile with benzene will give us a bond here. So this is an azo bond, an azo group. We have an idea, the presence of azo group generates color, produces color. As I've told you just a moment ago, this benzene can be simpler. It could be something like that. It could have been substituents around it. So by changing of the substituents, by changing of the number of rings, one can produce a variety of colorants, variety of color molecules. So this is how diazonium compounds, diazonium ions are important for the preparation of textile dyes. They could be made to react as electrophiles in different reactions with benzene to produce new azo compounds, which are supposed to be in fact colorants. So this is an extremely good example for undergrad students who want to know, who want to learn the electrophilic substitution reaction of aromatic compounds, and it is an extraordinary examples for students who are practically working in labs for the preparation of certain textile dyes and colorants. They can use electrophilic reactions as the diazonium ions as electrophiles for electrophilic substitutions for the preparation of some functional colorant molecules. So this is what I was to explain here today. The diazonium compound, the preparation, the mechanism behind the diazonium compound, diazonium ions, how actually they produce. So if you have any question, you may put the question in comment area, or you may send me an email. I will try my best to respond at my earliest convenience. So thank you very much for your kind attention. Thank you very much again, please. Assalamu alaikum.